Okay, can we hear me? Good. So good afternoon, I'm Alex Vlachos from Valve. This is Advanced VR Rendering Performance. I'm glad a lot of you are appreciating the humor in the title slide. I asked one of our artists, Tristan Reedford, he's the artist who made the Atlas robot in the robot repair demo. I asked him if he could do something to take the focus off the fluorescent pastel colors. Not sure he succeeded at that part of it, but added some good entertainment anyway. So this is effectively part 2 of the presentation I gave last year. Last year I gave a talk at GDC called Advanced VR Rendering. This is sort of a continuation of my thinking about where I think VR rendering should be moving. The slides and the video from last year's talk is free online. If you haven't seen it, it's worth watching. It's a good primer for some of the things I'm going to be talking about, but it's not a prerequisite, so I'll cover the necessary pieces as I go from last year. So here's what I'm going to talk about today. There's 4 sections today. I'm going to talk first about multi-GPU for VR, specifically how we use 2 and 4 GPUs for VR specifically. Then I'm going to talk about two methods for reducing fill rate at the periphery. They're called fixed foveated rendering and radial density masking. Then I'll talk a bit about reprojection. I know us at Valve, we haven't said much about reprojection over the last year or two, and there's really no good reason for it, so I figured I'd cover what our thinking is on that and where we think reprojection fits into the pipeline. And the last section is going to be what I'm really here to talk about today, which is the adaptive quality system, and how to basically scale your renderer up and down to maintain frame rate and also give a better quality result. So one thing I want to mention before I get into the multi-GPU section, this is a slide from my talk last year. So if you're doing a standard stereo render, you'll get, this is coming straight out of your projection matrix. As it turns out, though, most of these pixels, about 15 to 20% of these pixels you can't see, you'll never see on the panels through the optics. And so we black out these pixels as we render. So as you see all the screenshots in this talk, they're going to have these pixels blacked out. So you didn't see my talk last year, that's why. We basically have this thing called a hidden area mesh, and it's a low polygon triangle mesh that we render into the stencil buffer or into near depth, and that'll prevent the rasterizer from actually spending time rasterizing all those pixels that you're never going to see anyway. Okay, before we talk about multi-GPU, let's talk about single GPU. Single GPU, obviously you got one GPU, it's going to do all the work, it's going to do all the rendering. That goes without saying. Stereo rendering can be done on the single GPU in a number of ways. I'm going to just show my example of sequential rendering, where we render the left eye followed by the right eye. So in a standard single GPU setup, this is a pretty traditional renderer. You're going to render your shadow buffer up front, and then your left and right eye are going to share those results because your shadows are view independent. So you render your shadow buffers, then you go ahead and render your left eye, then you submit your left eye to the VR system, and then you render your right eye, you submit your right eye texture to the VR system. And mind you, the blue jobs on this on the timeline are done by your application, where the gray jobs are done by the VR system. Sometimes we use the term compositor for that. And so you render shadows, left eye, submit left, right eye, submit right. Then the application renders what we call the app window or the companion window. And the idea there is that generally speaking, on the main monitor, there's a window that you're gonna render something to. It's oftentimes just a mirror of what's in one of your eyes on the HMD, but for sort of co-op experiences or for party games, there are developers that are rendering something completely different that's going to go on the main desktop for the people that aren't wearing the HMD to look at. So that's a variable amount of work depending on your use case. And then when the application is done, the VR system steps in, does all the lens distortion, does chaperone bounds, renders overlays, a bunch of other things. So that's a standard sort of single frame. One thing I want to mention is that when you submit the left eye and right eye render textures to the VR system, there may or may not be GPU work that happens there. So it's a good mental model just to assume a little bit of GPU work's going to happen when you submit your left and right eye textures. It's a good way to at least plan for something to happen if the VR system needs to do something. All right, so there are 2 multi-GPU Affinity APIs. AMD and NVIDIA each have their own API, and they're very similar. They both try and accomplish the same set of goals. Basically, there's an Affinity mask. And there's a bit in that mask for each GPU that's live in the system, and you set your mask and you make draw calls. And those draw calls are going to be broadcast to all the GPUs that have their bits set. So you have 2 GPUs, you set your bit mask to 1, and you draw, it's going to go just to the first GPU, you set it to 2, and draw to go to the second GPU, obviously you set it to 3, and your draw call gets broadcast to both GPUs. So It's pretty straightforward. The way you get stereo rendering is you can set constants differently per GPU. So you can set different constant buffers, whether it be the contents of the constant buffer or constant buffer handles. It depends on which system you're using. But effectively, you can set that up. And then there's API calls to transfer subrects of render targets across GPUs. So in a dual system, in a dual GPU setup, you're going to render to both GPUs, and then you're going to transfer one of the GPU's results back to the primary GPU. And there's also APIs to have transfer fences, so you can asynchronously do that transfer while the destination GPU is rendering something else. So let's look at what two GPUs looks like for VR. This is pretty obvious. You've got two eyes, two panels in first-gen HMDs. So each GPU is going to render a different eye. Okay? GPU 0 renders the left eye, GPU 1 renders the right eye. The first thing you're going to notice when you look at the timeline below now is that the shadows are going to be redundantly rendered on both GPUs. You can't really share the shadow results across GPUs because they're being rendered independently. Now, you could think about playing games here and try and split the shadow rendering cost between two GPUs and then have them transfer their results back and forth. But you're going to end up adding complexity to your pipeline, and it may not be a perf win because transfers do cost. It takes time to transfer. So for this talk, just assume we're going to do the shadow rendering up front. And so what's going to happen is you render your shadows, both GPUs go off render shadows redundantly, then the left eye and right eye are going to render in parallel. And this is where your big savings is with a two GPU system. Now after GPU 1, after the right eye is done rendering, you're going to want to transfer that render target back to the primary GPU to GPU 0. And if you're doing MSAA rendering, you want to do your resolve before that transfer, because the transfer for a standard resolution render target, the recommended resolution will take about a millisecond, give or take. So if you transfer an 8x MSAA render target, it's going to take you 8 times as long. So you want to make sure you do resolve before the transfer. Now what you'll notice is that because we can use asynchronous fences, we can use transfer fences, as that transfer is happening back to GPU 0, we can sneak as much work as we can fit in that bubble of that transfer. So that's where we'll submit the left eye render, because it's already done, and do any of our application window rendering, that companion window. So we can hide that work in the bubble of this transfer. So we're not spinning idle on GPU 0. There is going to be a bubble. After your app window's done rendering, the GPU 0 has to wait for the transfer to come through, then you submit your right eye, VR system takes over, does its rendering. Overall, with the same workload, you're only getting about a 30 to 35% perf boost. And that's because the entire frame's not double. You're not getting double the performance, right? Shadow rendering happens redundantly. The work at the end of the frame still has to happen with submission and your app window, and the VR system has to step and do its work. So, and there's going to be a little bubble from that transfer. So it's not a doubling of performance, but you do get about a 30 to 35% perf increase for the same GPU workload. Let's look at 4 GPUs. Now there's a few ways you can split your view for 4 GPUs. This is sort of, I think, to me, the most obvious way to do it. You split each eye in half vertically. So you have each GPU is rendering half of an eye. The reason we're going to split vertically, by the way, not horizontally, if it's not obvious, is if you think about an outdoor rendering, if you're standing outside looking at the horizon, the top half of your screen is going to be the sky, the bottom half is going to be all the expensive stuff. So we generally tend to split vertically so you can get a more even workload. So again, you're going to have all 4 GPUs redundantly rendering those shadows up front. There's no savings there. It's going to cost you the same. And again, you can try and play games with transferring results back and forth. Good luck with that. I don't want to do it. Unless your shadow rendering is really expensive, I don't really think it's worth the effort, but you can experiment with that. Then your big savings here, your 4 GPUs are going to be rendering half of an eye in parallel. Keep in mind that you're going to render half the pixels per GPU now compared to a 2 GPU setup. However, it's not a necessary doubling of performance per GPU because, at least for Source 2's implementation, we are transforming the same number of verts on all 4 GPUs. I'm broadcasting every draw call to all 4 GPUs. And yes, we can be smarter about trying to cull for objects that are fully within the left half or right half of each eye and set your affinity mask per draw call. Our architecture turns out to be very tricky and nearly impossible to do that. So instead, we just broadcast to everyone. So the transform cost is the same, but we do have half the fill rate per GPU. So after you're done rendering, there's a number of ways to do these transfers to get all the results from the other 3 GPUs back to the primary GPU. And the method we think, and when I say we, I mean NVIDIA and AMD, I've had a bunch of discussions with them. The way we think the right way to do it is this, is you want to first get your left eye fully composed on the primary GPU. So transfer GPU 1 back to GPU 0. Get your full left eye there. Once that's in place, then start your transfers of your two right eye textures. While in that transfer bubble, again, you can submit your left eye, do your app window rendering. When the right eye transfer is complete, that's when you can submit your right eye, let the VR system do its work. One thing to keep in mind is that, depending on the driver architecture, 4 GPUs might actually cost you quite a bit of CPU perf. Even though you're only doing one submission across four GPUs, the driver might be doing a bunch more work. So be conscious of that. Make sure you're looking at captures and be aware of what the drivers are doing. So the transfer at the bottom, there's other ways to transfer from 4 GPUs back to the primary. The bottom one is what I just talked about. The top two are just two other options. You can either, the first option up top is just kick off all 3 transfers, let them happen in parallel. It depends on the hardware, it depends on the drivers, whether that's a win or not. Another way is just sequentially do it, just give each GPU exclusive access to that bus to transfer over into GPU 0. Which one's faster? It's hard to say. Drivers are still coming in hot. They're sort of, they're still working on performance. So there's a bit more. I would say give it a few more months and keep timing these things and figure out how the drivers are behaving from both vendors. We think the third option at the bottom is the right way to do it. So if we kind of summarize that, if we look at these 3 options side by side for the same GPU workload, single GPU, let's say it fills almost 11 milliseconds. Dual GPU is going to give you about a 30-35% savings. And the disappointment here, it feels like a disappointment, is that 4 GPUs is only another 5 or 10% on top of that. Now, granted, I drew these graphs, but this is based on GPU view captures of what's actually happening. But I think this is the wrong way to look at the data. Because if you look at the data this way, you're going to think, well, I'm not sure if 4 GPUs is worth even writing the code for, because it's not a huge savings. But this is not the right way to look at the data, I think. I think this is a better way to look at the data, which is, instead of looking at the same workload in all of these situations, you want to look at it and say, well, for 11 milliseconds, what can I get done for a single GPU versus dual GPU versus quad GPU? And the difference here is that when you go to a dual GPU, you can likely rasterize twice the number of pixels as you can in a single GPU setup. And in a quad GPU setup, you can do 3 to 4 times the number of pixels. So you're going to end up with a much higher quality, higher fidelity render when you have those extra GPUs. And this is what the adaptive quality system aims to accomplish, that I'll talk about in a few minutes. And that's about how you can scale up your rendering quality depending on the GPU cycles that are available to you. So without an automated system to do this, it's a much more difficult task to try and fill the GPU and make use of all those extra cycles. But the adaptive quality system is going to try and accomplish that. So that's multi-GPU rendering. It's pretty straightforward stuff. Just wanted to share that, give you a good mental model of how to think about multi-GPU. So these are 4 topics. So that's the first of the 4 topics. These first 3 topics I'm talking about, I'll come back to when I get to the adaptive quality system later. Now, this section, I'll be honest, I really have way more than an hour of stuff to talk about, but I'm going to try and keep it to an hour. I had to make a decision a couple days ago whether I cut this entire section or just speed run through it. So I'm speed running through this section. I'm going to go through it quickly. I dropped some of the details. You guys are smart. You'll figure out the details. It's not hard. But I wanted to share this idea because we have this big problem with there's this difference. There's this sort of the projection matrix and our VR optics are at odds. They want their pixel density distribution to be different or actually opposite. And what I mean by that is the projection matrix wants a higher pixel density per degree at the periphery versus the center of your screen. If you think about how a projection matrix spreads its pixels out, where the VR optics want all your pixels in the center and very few pixels per degree at the periphery. So you're actually rendering the opposite pixel density that we want to show on the panels ultimately. We are over-rendering pixels at the periphery without question by a lot, potentially 2x or even more depending on the optics. So let me just recap. This is another slide from my talk last year about over-rendering. So this is your raw left and right render target that comes out of the projection matrix. And this smaller texture is how it gets warped before we put it on the panels of the HMD. And what you'll notice is the center 50% is about a 1-to-1 pixel to pixel ratio. What we're rendering in the middle and the bigger texture matches covers almost the same area on the panels, where that outer ring of pixels gets squished significantly. If you look at the door all the way on the right, if you look at the ceiling tiles, everything gets squished down. So we're over-rendering those pixels, and they actually matter less. The things you really care about are the pixels right in front of you. So as I was looking through this, I'm trying to think of ways to reduce the fill rate in that outer ring. And so one idea is fixed foveated rendering, we're calling it that. It has nothing to do with eye tracking. If you think about Microsoft's foveated rendering paper, if you've read it, it basically, with eye tracking, depending on where you're looking, it'll render the pixels right in front of you at very high resolution, and then as you get farther and farther away off axis, you render lower resolution images. So if we instead fix the center of that view on the center of the optics, we can try and take advantage of the same idea where we can render the outer ring of pixels at a lower resolution compared to the inner circle of pixels. So if we instead render this image to 4 viewports and then reconstruct the image on the right, the thing we really need, you can actually rasterize far fewer pixels. And what's going on here is the 2 circles at the bottom are full 1-to-1 resolution with what's on the right in the center of the screen, and the pixels on the outside, on the exterior, are rendered at, say, half resolution or less, and then we scale those pixels up as we bring them in to the main renderer. And one thing to point out is that there's an additional occlusion mesh that I use to block out all the pixels in the center circle, because you're not going to use those pixels. We're going to pull the pixels from the middle from the high resolution render below. Same thing for below. We're going to chop off the corners because we're not going to use those pixels anyway. The way this maps is to the final image is those center high resolution green pixels come from the bottom circles, blue pixels with lower resolution come from the lower resolution circles, and the red pixels are a blend, an interpolation between the high res and low res pixels, so there's no harsh discontinuity. There's some obvious ways to use multi-GPU for 2 and 4 GPUs for this. Obviously, you have 4 GPUs, you've got four viewports, it's pretty obvious. And you can get a nice perf win if you use NVIDIA's multi-resolution shading, which is also called the fast geometry shader. We can easily gain another 5 to 10%. I don't have time to explain what that is, but Nathan Reed from NVIDIA has done a great job talking about that at SIGGRAPH last year in his GameWorks VR session. And NVIDIA's got plenty of information on their website about that. So that's fixed foveated rendering. I had an idea to do this, and sometimes I'm bad at words. I'm bad at describing things to people in the office. So I tried to describe that, fixed foveated rendering, to people in the office. And I said, hey, I've got this idea. It's based on Microsoft's paper. It doesn't really use eye tracking, but anyway, I explained it. And Jeet Barnett, who was one of the original Portal team members, he worked on our orbicular drop. I can never say that right. Back at DigiPen, super smart guy, really great gameplay programmer. He's not a rendering specialist, but he's really well versed. And so I explained it to him, and he said, really, that's really interesting. So I went off and I wrote the code for fixed foveated rendering, came in the next day, showed a demo. And I was showing everyone how it worked. And Jeep goes, that's not even close to what I thought you meant. And I said, well, what did you think I meant? I'm sure I explained it pretty well. And so he goes, well, what I thought you said was you're going to skip pixels like every other pixel as you get farther away from the center of the optics. I was laughing. I'm like, that's not how GPUs work. You can't just skip pixels. GPUs operate on 4x4, on 2x2 pixel quads. And so if you touch one of a pixel in a 2x2 quad, you're paying the cost for the whole quad. That's how GPUs work. So, anyway, later that night I'm sitting around and I'm thinking back to what he said, and I realized, I'm like, wait a minute, that's actually a really good idea. Let me try that. So that gave birth to this idea of radial density masking. And the idea is that instead of rendering to 4 viewports, inner and outer rings, you just render your normal stereo image. And that outer ring that looks darker, the reason it's darker is because we're going to skip rendering a checkerboard pattern of 2x2 quads of pixels. Okay? And if I zoom in on that, every black square in that checkerboard pattern are 4 pixels, and they're aligned with how the GPU rasterizes, right? GPUs work on 2x2 quads of pixels. If you touch one of those pixels in the quad, it's the same cost as 4 effectively. That's how you should think about it. If you skip all 4 pixels, it's pretty much free. Well, it's not free, but it doesn't cost you, there's no overhead there. So the idea is for that outer ring of pixels, we can reduce our fill rate by 50% by skipping 2x2 quads of pixels in a checkerboard pattern. But we're going to need a reconstruction filter to fill in those holes. So here's the first reconstruction filter I've tried. It's a pretty straightforward one. There's obviously better ways to filter this data and fill in those holes, but I'll show this because it's a simple one that took me an hour to do. It's really easy to explain. So the idea is for the pixels you didn't render, take the 2 nearest samples that you did render and average them. That'll fill in all those holes nicely, but you're going to end up with this really weird, jaggedy, toothy looking pattern because you're going to be pulling black pixels down, bright pixels up. It's going to look kind of strange. So if you then also average across the diagonals, right, for each pixel you did render, average it with its nearest diagonal neighbor, you end up with what looks like this, which is a really low resolution, blocky render, but you don't get any jaggy effects. And if you then take that and do the world's simplest 3x3 blur filter, you'll end up with what looks like this. And this surprisingly looks nearly identical to what fixed foveated rendering looks like, where you render at half resolution and then scale up. So I'm pretty happy with the quality of this as a starting point. Again, this is the initial prototype, but there's a lot of steps here, so we can optimize this in the obvious way everyone here probably knows, which is you can optimize this by just figuring out what an optimal set of bilinear texture fetches are on the GPU. And so you can, for every pixel you didn't render, you can instead take 4 bilinear samples out of that texture with very specifically placed UVs and then apply these 4 weights to them. Same thing for the pixels you did render. You can take 5 bilinear samples, set their UVs very specifically, and set their weights below. And that is the same exact result as you'll get by doing the multi-stage approach on the left, and it's at the cost of about 4.5 samples per pixel. So that works really well. Radial density masking it's a good way to reduce fill rate. The idea is that you're going to clip these 2x2 pixel quads as you render. You can do this at the top of your pixel shader by calling the clip function, or you can fill your stencil buffer or depth buffer up front with that checker pattern, but be conscious of hierarchical Z and how GPUs work. It could actually cost you more to do some of these things, but implement it, time it. Of course, you have to do the reconstruction filter. Now, for aperture robot repair, for the demo we showed last year, I'm going to show a bit more of that today. It's about a 5 to 15% performance boost by doing just that. And I'm pretty sure you can get higher gains depending on your content, depending on your shaders. But it's pretty much a win overall. It's worst case scenario, I've seen it be just a wash. It didn't buy you any perf, but generally speaking, it's a good win. It's really a win on low-end hardware. And what I mean by low-end hardware, I'm talking about hardware that's even below what we consider the recommended spec of GPUs. So, all right, so those are those 2 techniques. I don't have too much time to talk about them more, but that's just a good primer. I think something to think about. How do you reduce fill rate at the periphery for those pixels that we are over rasterizing by default? So let's talk about reprojection just for a few minutes. Reprojection is something that is the best method we know of today for dealing with dropped frames, for dealing with missed frames. Okay. If your engine's not hitting frame rate, the VR system, the underlying VR system, really only has one option to fill in that dropped frame, and that's through reprojection. Now, by reprojection, Oculus uses the term time warp to refer to rotation-only reprojection, I believe. I hope I don't have that wrong. And then, but there's also ways to do position and rotation reprojection by using a depth buffer, which I'll talk briefly about. Reprojection is fine for filling in missed frames, I think, but you really should think about that as a last resort safety net. You absolutely should not rely on reprojection to maintain frame rate on whatever your application says is the min spec. If you tell your customers, this GPU is our min spec, you should not rely on reprojection to maintain frame rate. I think that's a bad idea, because there's artifacts, visual artifacts that come with reprojecting. So let's talk about that, because I think it's important to discuss what the side effects are of reprojection, so you can make good choices about when you think it's okay for your application to use it. So the most obvious artifact is judder. Hopefully everyone here already knows what judder is. The idea is that anytime there's animation, you're rendering at half frame rate and you're filling in every other frame with a reprojected frame, you're going to get what looks like 2 ghost images overlapped. And and we call that judder, and that you can get that either from the camera translating, if as the user you're moving around, translating, squatting, standing, you're going to see a ghost image of what's in front of you. If you're standing still and something's animating in front of you, the animation's going to have basically 2 clear ghost images that are overlaid. And the farther apart those ghost images are based on how much movement there is. And of course, if you have track controllers and you're holding stuff right in front of your face and moving it around, they're going to ghost pretty badly too. But it's not that obnoxious. It's a ghost. It's not as bad as actually rendering at half frame rate and not reprojecting. So that's a known side effect. That's not as big of a deal, I think, as these next issues. These side effects are the ones that sort of worry me more. It's the more subtle side effects of reprojection. And the idea is that when we talk about rotation-only reprojection, if you don't really take the time to think through what that means, you might misunderstand what's really happening. And so when you reproject, the reprojection is eye-centered, not head-centered. Your head, when it rotates, is head-centered. And so when you render an image, so this is a top-down view of 2 eyes and what they're looking at. And this is our left and right virtual cameras rendering their parallel frustums. Now when you if you're going to reuse the output of those rendered frames as you rotate your head, what's going to happen is your eyes are going to change position as your head's rotating and looking left and right. In this example, it's an extreme rotation, but what happens is, you can see really clearly, is that we're using those frustum that we rendered with, they're frozen in time. Those images are rendered. We want to reuse them. So what's happening is you're actually fetching from images that were rendered for one eye, potentially from in front of your left eye and from behind your right eye. And this is really bizarre if you think about it from a rendering perspective, that there's this sort of scaling effect that you're going to get. The more rotation that there is in your reprojection, the more of this really subtle scaling artifact you're going to get. So I'm worried a bit about that as far as the reprojection effects, but not as much as this next thing, which is your ICD. So IPD is how far apart your eyes physically are. Your ICD is your inter-camera distance. It's your virtual camera separation that you render with. Generally, you set your ICD to be the same as your IPD, right, as your physical eye separation. So in this example, the user has 64 millimeter separation of their eyes, so you set your virtual cameras at 64 millimeters apart. Now, in the same extreme rotation as above, if you rotate your head, which looks like maybe about a 10 or 15 degree rotation, what's going to happen is that ICD is going to artificially narrow. If you take the two vectors that are pointing straight ahead of those eyes, they're going to be artificially narrowed. And so what happens is the more you're rotating, the more you're reprojecting, the more your ICD, your virtual cameras, are artificially narrowing and widening. And I'm worried about that effect on the human visual system, on your perception system, also known as your monkey brain. And I'm worried about what that does to users long term or over long periods of time. So we tend to think about rotational reprojection as something that we really just want to use to fill in dropped frames occasionally. And when you think about how bad of an error is this, so Mike Abrash, in one of his Valve blog posts in 2013, I think had a really good statement, which is a leisurely head turn is in the ballpark of about 100 degrees per second, which is about this, and you can obviously rotate faster, 200 or 300 degrees if you're whipping your head fast. And if you reproject just one frame, you'll probably go 2 or 3 degrees, worst case. If you're going to reproject multiple frames in a row from that same render, that's going to double. So you can easily start reprojecting 5-6 degrees or more. And that's where I start to get worried about these subtle side effects of reprojection. So those are the side effects, but there's good things about reprojection. Obviously, it's a well-understood algorithm. We've known it for decades. It's not, it might actually improve. There's people looking at ways to improve rotation-only reprojection given these side effects. It works reasonably well for a single missed frame. It just does. There's, even with those side effects that we're aware of, for filling in dropped frames, it works reasonably well. And my personal statement is that there's clearly a non-trivial set of trade-offs, but I think it's good enough to use as a last resort safety net to fill in dropped frames. It's better than dropping frames and rendering at 45 hertz. That goes without saying. I hope everyone in this room already agrees with that. Rendering at half frame rate is not shippable, it's not showable. It's very uncomfortable to your users. So it is a usable solution. Positional reprojection is one that's a little trickier. I'll just touch on this lightly. It's obviously, I think, it's still an unsolved problem to some degree. We're super interested in a solution to this, because if you can do positional reprojection and you can actually take into account the new positions of the eyes and the head as you're moving and effectively have a depth value per pixel, that's going to produce a better result. But there's some issues, right? In a traditional renderer, you only get one depth value per pixel. So if you have translucency, like particle systems, good luck reprojecting that. They're going to be set at the wrong depth. Okay, so you can't just use a traditional renderer and have it just work magically. There's issues with translucency and depth there. Another subtle problem is if you're using MSAA, your depth buffer is going to be stored as multiple samples per pixel, but you may have already resolved the color buffer. So now if you try and reuse that resolved color buffer with those separate MSAA rendered samples, you might get color bleeding. If you have a near surface and far surface of very different colors, they're going to blend together, and when you reproject, you're going to get color bleeding across surfaces that are nowhere near each other in space. Hole filling algorithms, obviously, as you move around and you start peeking around corners, or you squat or stand and you look over surfaces, there's going to be pixels that you have no data for, so you have to invent a color for those pixels. We call it hole filling. And you have to be very careful, because a lot of these algorithms can cause retinal rivalry, which means your eyes can't stereo fuse those colors because they don't match. And so it's a very tricky problem. It's a hard problem to solve, but it's something we've been thinking about, because it's that'll have far fewer side effects than doing rotation-only reprojection. So then there's asynchronous reprojection. Asynchronous reprojection is the idea is that you can have a job on the GPU that, let's just say, half a millisecond before vsync, no matter what's going on, the GPU gets interrupted, you preempt the GPU, and if the currently rendered frame is not done, it can take last frames, left-right stereo pair, do a reprojection, rotation-only reprojection, and display that, and then let the GPU continue on finishing the last frame. We think this sounds like the silver bullet, the ideal safety net. If you have a system like this, then we can practically guarantee that we never drop frames on an HMD, which is super critical for consumer VR. But it requires preemption granularity on the GPU that's as good or better than current generation GPUs. I meant to ask AMD and NVIDIA what I can and can't say about their GPUs publicly, so I'll stick to what I believe they've already said, which is current GPUs, current generation of GPUs, we can think of it as you can generally preempt to draw call boundaries. It's not entirely true. You can go a little slightly finer, I think. But you can preempt to draw call boundaries. That means if you want to step in and reproject at the end of a frame, and your VR system says step in half millisecond before vsync or 1 millisecond before vsync, if there's a really expensive draw call happening, like you have a 2 millisecond post-process call, well, what's going to happen is it won't be able to preempt in time and you're going to miss vsync. So there's really no guarantee with current GPUs, the way you can preempt, the granularity, there's no way to actually guarantee you can preempt and get there in time. You have to play a lot of games with timing. So the applications have to be aware of preemption granularity for current gen GPUs for asynchronous reprojection to be a real option. And I think Nathan Reed from NVIDIA had a great thing to say at GDC last year. His statement is, if you think about post-processing, if that is an expensive draw call that could be blocking and not allowing preemption to happen, break your post-processing up into a bunch of smaller triangles and render triangle at a time with individual draw calls, right? Give the GPU and give the drivers more opportunities to be preempted. But again, there's situations where you have track controllers, right? I can go and pick up something the size of a marble and put it right in front of my eyes, and now that's a full screen render of this little object that you wouldn't have imagined would be full screen, and that marble could be really expensive to render. So, there's no great solution yet until GPUs can be preempted instantly. We're at a much finer granularity anyway. So we have this thing called an interleaved reprojection hint. So the reality is there are going to be GPUs and older GPUs that we care about that cannot support asynchronous reprojection. So we need something else. We need an alternative. And so we have this idea. So we have this. We just added this to the OpenVR API recently. It's an interleaved reprojection hint, and it's a hint in that we can request that the VR system opt into an every other frame rotation-only reprojection if the underlying system doesn't support asynchronous reprojection. That's why it's a hint. The Valve programmer that's been writing all of this code, his name's Aaron Leiby, he's done a really interesting implementation of interleaved reprojection. It's incredibly detailed and tricky to get right. There's a lot going on in how you predict properly where you reproject, what your timings are, and he's got this to what I think is a really optimal implementation where instead of having 11 milliseconds for a frame, when you opt into this, you end up with having almost another 2/3 of a frame at your disposal, so you have about 18 milliseconds to render. So this is a great safety net. It's a good bottom of the barrel. Once you're at the bottom of your quality level, we'll talk about adaptive quality in a minute, you can opt into this and buy yourself an additional 7 milliseconds to render. So we think that's a good safety net. And it's also a safety net that the runtime could opt into, could automatically turn on when it detects your app's about to drop frame rate. We can just force this on if there's no asynchronous reprojection support on the GPU that you're rendering or in the underlying system. So it's a good trade-off, I think. It's a good trade-off, and I agree with what Michael Antonov from Oculus said last year. He has his blog post from March 2015. If you haven't read it, read it. It's a really good post. It's titled Asynchronous Time Warp Examined. And what he's saying here in this paragraph effectively is, I'll summarize it here, is asynchronous time warp should run at a fixed fraction of the game frame rate. Meaning, if you're at 90 hertz refresh rate on the HMD, you either want to hit 90 hertz or fall down to the half rate of 45 hertz. And this is going to result in image doubling, judder, but the image doubling is going to be stable because it's the same separation frame to frame. If you target some intermediate frame rate or a variable frame rate, that judder ghost is going to jump all over the place, and it's going to be a far worse effect. So I think everyone's on the same page here that an interleaved reprojection, that approach is the right approach to fill in drop frames if you need to use that. All right, well that's what I want to say about reprojection for now. I'll come back to that in a little bit. Now let's talk about adaptive quality. This is what I really want to talk about. So, and I'm going to pull those other three sections into this. So maintaining frame rate in VR is really hard. It just is. It's way more challenging than non-VR rendering in my opinion. And the reason for that is because there's two main reasons. The first is that the users have fine control over where that camera is. If you think about a traditional game, first-person shooter, you're pretty much a standing height or crouching height, and you're moving in a plane. And it's pretty easy to figure out all your perf problems. And you also have this big bounding, bubble around you, so you can't really walk up to walls that close because we're good at our jobs. And but there's limitations that help us and makes it really easy to keep frame rate. In VR, users can put that camera anywhere they want. They are fully tracked in that space. A couple weeks ago, I was laughing. We were giving a demo, and someone was looking at the robot repair demo. And I look over at the guy, and he's literally laying on the floor, looking up at Atlas. Like, what are you doing? What are you doing? I just want to see what it looked like from down here. I was like, great, I have no idea what the perf is down there. I've never done that. Other people have come through the office that are like almost 7 feet tall, looking down at Atlas, and I'm like, oh, I don't know what that perf's going to be like. I've never tried that angle, right? I'm not that tall. So the users have a lot more control over that. And additionally, we have track controllers. A lot of experiences are letting users effectively reconfigure their environment. With track controllers, you can pick up objects, move things around, and if you put 100 objects scattered around a room, someone's going to take all 100 of those objects, make a pile of all those objects, and shoot a rocket at it, just because it's going to be fun, right? And so it's hard to anticipate performance. It's hard to really fine-tune performance in your engines in VR because of the interaction models that we're moving to, especially with track controllers and being able to move things. So I have personally given up on trying to tune a renderer and content to hit 90 hertz. I went through that pain last year. We showed robot repair last year at GDC. We haven't really changed the content or shaders at all since then, by the way. It's the same demo. But before GDC last year, I spent a ton of time, and everyone in the room's done this, you take the worst 20% of that application, of that experience, and you tune your performance of your renderer, of your code, to hit frame rate for the worst case scenario. And the other 80% of your experience is in frame rate. It's not a big problem, right? The problem, though, is that was barely hitting frame rate on 980. It maintained frame rate. I didn't fail. It hit frame rate, fine. But if you dropped any lower GPU in that and run Aperture on it, it wasn't going to hit frame rate. And so thinking about how to manage that and get to a shippable solution led me to think more about this adaptive quality system. And so that worst case 20% is what really drives our decisions usually. So I wanted to think about this differently. So adaptive quality, to state it simply, it's a way to dynamically change rendering settings. I'll explain what that means in a second. Rendering settings to maintain frame rate while also maximizing GPU utilization. You want to be able to scale up, right? So there's two goals with this. The first goal is to scale down, to be able to reduce the chances of dropping frames and having to reproject. If you can reduce your quality a certain level, that will allow you to maintain frame rate in your worst case scenario or on lower end GPUs, it's going to be a big win because visually you don't want to reproject. You want to avoid jitter. You want to avoid all these other subtle artifacts unless you absolutely need to use it. The second goal is on the other end of the scale, is you want to be able to scale up and increase quality where you have GPU cycles to spend. The example I'm going to use today is that robot repair demo. It's going to be running, and I have two methods for having it run in frame rate on an NVIDIA 680. It's not a typo, 680. That's a 4-year-old GPU. I use that. I keep that on my second machine all the time. That's a good way to vet every decision you make. If you can get your stuff to work on a very low-end GPU that we don't even consider it a min spec, it's below the min spec. But if I can maintain frame rate with complex data sets on that GPU, we're going to be doing fine on the GPUs that we actually care about. So I'll talk a bit about that. So the benefits of this, some of them are obvious, some of them are not. Obvious benefit is you're going to have, if you have this adaptive quality system, it will lower your min GPU spec. You'll be able to run on lower end cards that you would have otherwise. Aperture, without changing a line of shader code or a single art asset, we're now running on 4-year-old GPUs. GPUs that are 4 years older than what we showed last year. And that to me is pretty amazing. That's a huge benefit. There's also this increased art asset limit. Basically, artists now have more control. They're less limited by the renderer. The artists now get to make the trade-off of, if they want to use more complex materials, throw more geometry at a scene, at an object, instead of just dropping frames, they're just going to automatically get a slightly lower quality render. So it's up to them to kind of balance that and make that trade-off, right? Effectively, it's not my problem anymore. They get to solve that. So they can manage what that trade-off is. And obviously you won't need to rely on reprojection to maintain frame rate as long as you're within your min spec. because you're going to dynamically and adaptively change your render settings to keep frame rate. Those are the expected benefits. There was one unexpected benefit that I did not anticipate until I implemented it, which I think is the most important one, is the best benefit. And that is that our apps look better across the board. So again, last year I perf-tuned the hell out of Aperture to get that worst 20% in frame rate on a 980. Running on the same hardware on a 980 today, Aperture across the board looks better, because the other 80% of that experience, so where there's GPU cycles to burn, we're now automatically increasing the rendering quality on the fly. And so overall, Aperture looks higher quality, higher fidelity on the same hardware that we were barely in frame rate on last year. And yes, that 20% is still barely in frame rate, but it's now auto-tuned to maintain frame rate and guarantee that you're going to hit frame rate. So what settings can you and can you not change? I'll show you a video in a minute that's going to show you how rapidly we're going to be making quality changes. But the things you can adjust are things like, you can't just turn specular on and off, turn it off at the low end and turn it back on the high end, because it's going to pop on and off really bad. You can't toggle shadows, because as you look over here, you don't want shadows to turn off, and you look over there and shadows turn back on. That's going to look terrible. The things you can adjust are things that you can adjust discretely or continuously that won't cause you artifacts. You can change your render resolution or your viewport size inside of a larger render target. We call this dynamic resolution. Halo 5 had a version of this last year. A few other games in the industry have done dynamic resolution in some form or another. It's not super common, but I think it's becoming more common. We can change our MSAA level or your anti-aliasing algorithm. So at the high end of our scale, we want to scale up to 8x MSAA. At the low end, we want to scale down to 4x MSAA. And of course, we have these new utilities like fixed foveated rendering, radial density masking that we can turn on and off at different levels. I tend to use those, like radial density masking, at the low end of the scale, because it's a nice sort of big hammer to hit low-end GPUs with. Just kill a bunch of pixels at the periphery and get the fill rate savings there. Here's an example of an adaptive quality scale. It's a discrete scale. It's not continuous, although that's the next step, obviously, is to investigate doing a continuous scale. But a discrete scale, we have a default level 0, 4x MSAA at a resolution scale of 1, and that will basically use the recommended render target scale from the API, which is 1512 by 1680, currently on the Vive. And as we scale up, we'll scale up the rendering resolution all the way up to 1.4x in each dimension, and we'll also increase MSAA to 8x. And on the way down, we'll go to a lower resolution. We're going to stay at 4x MSAA, because anything less, in my opinion, anything less than 4x MSAA, alias is horribly bad. So I like to bottom out at 4x MSAA. To me, it's a better visual to go lower resolution with 4x MSAA than higher resolution with 2x MSAA. And then at the very bottom, I turn on radial density masking, because that means you're on a really low-end GPU or on a horribly fill-limited scene, generally speaking. So this is a video. This is a capture of the Aperture robot repair demo. There should be no spoilers in here. The visualization you're seeing across the top, that's a visualization we have inside the HMD for artists to look at to see what the cost of their scene is. And what happens is each box represents one of those discrete levels on that scale. And the more to the right the boxes light up, the higher fidelity we are. The more to the left, the lower fidelity. The first green box around the middle, right around there that we just passed by, that's the default resolution. That's a 1.0 scalar 4x MSAA. Anything above that is going to be higher resolution, higher MSAA. I think the second box represents what we showed at GDC last year, at basically a 1.0 scalar 8x MSAA. So we can scale all the way up now. And what you'll notice is that as you look at these really cheap areas at wall, and by the way, this GPU, I forget which one, I think it was an NVIDIA 970, but it was sort of near the recommended spec, or maybe slightly lower, I forget exactly which one it was, sorry. But as we're looking at more expensive shots, the resolution drops down. As you look at cheaper shots, quality shoots up. So hope that's clear, right? Walls blank, shoots up. Look at the more expensive stuff, it drops down rapidly. And so that's why you can't really toggle on and off shadows and specular. It's going to be really obvious. So before we talk about how to do that, how to change quality, you have to figure out, you need to be able to measure your GPU workload accurately to make a good decision about when to drop down quality levels or increase quality levels. You have to keep in mind, your GPU workload is not always solid. There might be bubbles in there. And even on top of that, the VR system's GPU workload, there might be bubbles between your jobs and their jobs on the GPU. So you actually have to get the timings from the VR system. You actually don't have enough data in your application. You don't have enough visibility to the GPU to actually get an accurate timing to drive this algorithm. You have to get it from the VR system. And here's why. Here's a GPU view capture of a single frame. The orange workload in the middle is your application doing all of its rendering. And what you'll notice is that right before your application has, takes over the GPU, and right after, those green jobs are being done by the VR system. So there's a little thing that happens at the top of the frame, mostly to synchronize with VSync and a few other tricky things in there. And then at the end of the frame is where we do our lens distortion, we do we render the chaperone bounds, we do overlays, anything else that's going to happen at the system level. What you actually care about, you don't care whether your app has bubbles, there's a little bubble at the top of the frame, there's actually a tiny bubble right before the last orange job, before the green square at the end there. The thing you really care about is that end timer, or really the time remaining until the next VSync. That's the only thing you truly care about, is you want to dynamically scale your workload to keep that time remaining within some threshold. So you have to ask the VR system, because there's no way your application can get that timer. Only the VR system has the ability to get a timer at that point. It's the one that can put a GPU query there to figure that out. But one thing you have to keep in mind when you're thinking about this algorithm is you have to understand timer latency, and very specifically for how we predict in VR and how we're going to be rendering. So whenever you ask for a GPU timer, you're already one frame old. There's already one frame of latency in that timer. And you might actually have 1 or 2 frames in the queue that you can't touch. Meaning, as you detect that you're already about to drop frame rate, there might be 1 or 2 frames in the queue that are already rendering that you can do nothing about. So you have to be really conscious of this as you're designing the algorithm. So let's try and look at this visually. So this, there's a lot of data on here. So there's 3 rows. The first 2 rows are on the CPU. The bottom row is on the GPU. So the top row is going to be your gameplay simulation and your render prep. The next row down is going to be where you submit your D3D calls to the API, and then below the black line is the work actually executing on the GPU. So if we look at the green frame, at the start of the green frame on the game simulation frame, is we're going to ask for the GPU for its latest timer. And what we're going to get is we're going to get the timer from the blue frame that rendered in the past. You can't get the red frame's timer yet because it's still actively rendering. One thing to note, if you didn't see my talk last year, you should watch it, it'll explain it, but this is an algorithm called running start. I think Oculus calls it queue ahead or something like that. And so the idea is that 2 or 3 milliseconds before VSync, you want to start submitting your D3D calls to give the system enough time to actually start rendering after VSync. Anyway, watch my talk from last year, you can learn about that. But so the reason why at this point in time we're overlapping that red frame when we want to get the timer is because we want to start submitting early. So if you get that timer from the blue frame at that point, the top of the green frame, and you realize we need to drop quality levels right now, too bad for that red frame, it's actively rendering right now. And so if your thresholds, if you don't set your thresholds right or well, you could drop a frame without having any ability to stop that. So I'll talk about how to solve that in a minute. And depending on your architecture, that orange frame that's about to submit to its calls, you may or may not be able to apply a quality change to that submission thread. That's your render thread generally submitting the workload. Source 2, the way it's architected, I can't touch that frame. Everything's baked in there. I'm just out of luck there. So on source 2, I've got those 2 frames, that red and orange frame, I can do nothing about. If I decide we need to drop quality levels, it's too late for those 2 frames. But you can architect your engine to be able to step in and change quality on that render thread if you design for it. So here's the implementation details. Here's the algorithm. There's 3 rules. The goal of the rules is to maintain 70 to 90% GPU utilization. Meaning of that 11 milliseconds, I want to always be between 70 and 90% of GPU usage. That's the target I want to hit. It's about 7.5 milliseconds to 10 milliseconds, whatever that window is. So there's 3 rules to maintain that. The first is the high watermark, right? The 90% rule, which is 10 milliseconds. 90% of 11 milliseconds is about 10 milliseconds. And the idea is that we're going to decrease aggressively. If the last frame that rendered, that blue frame that we just queried and said, how long did that take? If that goes above that 90% threshold, I'm going to immediately drop 2 quality levels aggressively. And then I'm going to wait 2 frames before we even look at timers again, because for our engine there's 2 frames that still have the old quality settings. So it's useless data. So that's why I drop 2 levels aggressively, because there's 2 frames I can't touch. I've got to wait 2 more frames to make another change. On the low end, if we have 3 frames that, consecutive frames that are below the 70% threshold, which is about 7.8 milliseconds, I will then conservatively increase by 1 quality level and start bringing the quality back up. And again, you got to wait 2 frames because you have 2 frames in the queue that are going to be using the old quality level. Now, my hope was that this would be enough to solve the problem and everything would be great. There'd be no dropped frames. Not true. I could stand in the middle of the aperture room. I could look at the really cheap wall, whip my head around to the expensive wall, and drop a frame. Almost, I can find 3 or 4 contrived cases where I can force a frame to drop with these 2 rules. And I realized that because of those 2 frames that I can do nothing about, it's too steep of a challenge to maintain frame rate when you're looking at a really simple view to a really complex view. And as you whip your head around and all that complex machinery comes into view, it's pretty easy to drop frame rate. So I needed a 3rd rule that does some prediction. And the prediction is this. I'm going to use linear extrapolation to guess at what the next frame might cost. And linear extrapolation is just linear interpolation, but you're going to interpolate past your endpoint. And so I take the 2 most recent frames, and if the most recent frame is at least above 85%, it's getting close to being out of frame or out of our 70 to 90% window, but still a good frame, I'll use linear extrapolation to assume the same delta from the previous frame, and if that shoots past that 90% mark, I'm just going to I'm just going to assume it's going to actually be over budget, and I'll immediately drop 2 frames. And what that does is it gets rid of one of those frames that you can't affect, those red and orange frames. It basically reduces that number by 1. And having 10% headroom over that 90% is enough to swallow 1 frame. So that ended up solving basically every contrived case I could find to drop a frame in robot repair. And, you know, it depends on your render, it depends on the complexity of your shaders in your environment. You might need to tweak those thresholds slightly, but these thresholds work really well for almost everything we've been doing. And I'm pretty happy with them. So it's really simple. It's literally 3 if statements. The code for this is not complex. But the 10% idle rule is something that's important to mention. So the 70 to 90% threshold is set that way because I want 10%. I want about 1 millisecond of headroom to be able to poke into as I drop quality levels. Well, this nice side effect falls out of this, which is that you're leaving 10% of the GPU idle for other processes. It's actually not a bad thing. This is a really good thing. And trust me, the men and women on the driver teams at NVIDIA and AMD will thank you for this because they're just, thank God, right? What happens is, you know, you can't be greedy. You're not the only game in town. There's other processes that need slices of the GPU to do what they do. Even Windows Desktop needs a couple, 0.2, 0.4 milliseconds once in a while, every couple frames, to do its desktop compositing. So if you try and actually utilize all 11.1 milliseconds of the GPU, and even if you're within budget, you're going to drop frames because other processes are going to step in and steal GPU cycles, even if nothing's running, quote unquote. So my mental model of the GPU budget for VR has changed. Last year I stood up here and I said, you have 11.1 milliseconds. I don't believe that at all anymore. You really have about 10 milliseconds, and you're going to use that extra millisecond, you're going to share that extra millisecond with other processes and give you a little headroom to poke into once in a while. And so it's even a scarier view of VR, of how much time you really have on the GPU to maintain frame rate and not cause problems. So here's we have a few options in Aperture. I'll show you 2 of them. This is the first option. This is one way to maintain frame rate on an NVIDIA 680 in Aperture robot repair. And the idea is this is almost the same, I believe it's the same settings I showed earlier on an earlier slide. And the idea is that, the default level in the middle, that's bold, if you're on the recommended hardware like an NVIDIA 970 or the AMD I forget the number, sorry AMD, whatever the AMD card is, NVIDIA does a better job naming their products, I don't know, it's just easier for me to remember their number scale. But at that level you'll maintain frame rate in Aperture easily. If you put in 680 in your machine, it's going to use that bottom bin often, but it's never going to go below it, it's never going to drop frames. It will actually maintain frame rate at 6.5 scalar in each dimension, using radial density masking. But the other thing you'll notice is on a 680, it will scale up and hit the default resolution often. And so even on a 680, you're getting a really good visual most of the time, except for the really, really expensive shots. And if you put a really nice card in your machine, you put like a 980 Ti or an AMD Fury X, you're going to maintain 95% of your experience is going to be at this really high fidelity, high quality level. and everything looks much crisper. And if you put a 980 Ti in your machine and run Aperture, people look at it and take it off and go, this looks like we have higher res panels, because you're now super sampling, right? You're super sampling and multi-sampling. So, and that helps significantly in VR because of our ability to temporally recognize aliasing. But what about text? So Aperture turns out to not be a great example of designing these algorithms because there's nothing to read, there's nothing to look at. You're just looking at visuals, you're looking at objects. And when you have experiences where you have text in your environment, I'm not talking about overlays, I'm talking about text in your environment that have to be z-buffered in or depth buffered in with everything else you're rendering, you need enough textile density to be able to read things. And if you have an environment where you're going to shoot at something, you need to see detail far away, you can't go as low res as 0.65. It's too low res. Even though we can maintain frame rate, it's a good proof of concept, and it actually works fine for Aperture, it's not great for most experiences where you need to see details far away, you need to read text. So instead, my thinking is, we want to keep the low end, we want to raise the low end up to about 0.8 in each dimension. We found that if you target 0.8 in each dimension of the recommended render target scale, there's enough textile density there to design text to be readable in VR, at least for the first year or two. You might have text slightly larger in your environment than you might want, but it's not out of control. It's absolutely reasonable to manage. And if your GPU that you're on can't maintain frame rate at 0.8 in each dimension, maybe with radial density masking or fixed foveated rendering, then you can enable the interleaved reprojection hint that we talked about, right? And so for systems or GPUs that don't support asynchronous reprojection, there's this other safety net where you can tell the VR system, I'm pretty sure I'm going to drop frames in like any second now, go into this interleaved reprojection mode because I'm not doing well, I'm measuring that we're at the bottom of the barrel. So that to me is a different trade-off, and it's a last resort safety net. Reprojection is something we only think of that you want to use if you're below the min spec. If you tell your customers that's my min spec, don't try and avoid reprojection. You really shouldn't be reprojecting, except for the occasional dropped frame, which will happen no matter what. So here's option B on the right, which is now the text-friendly version of how to render Aperture. And everything's the same in the scale except three levels below default. Instead of going down to 0.73 scalar, I stay at 0.81, but I enable interleaved reprojection. And that's another way to maintain frame rate. I don't know which one we're going to ship with yet. Like I said, 680 isn't really going to be our stated min spec. It's just sort of my harsh test case that I use. And we haven't made the decision on the team which one to go with. But if I look at a 680, the trade-off is: are you happier with the lower resolution render with slightly more aliasing, or with the slightly higher resolution rendering but with judder? And that's sort of the trade-off you have to make for your experience is, do you need the textile density, or are you okay having slightly lower res rendering, and maintain frame rate without reprojecting? So one thing I want to mention is why is my scale maxing out at 1.4? Why aren't I going above 1.4? Memory. So on my adaptive quality scale, the high end uses 8x MSAA, the low end uses 4x MSAA. That means I have two sets of MSAA render targets. I have a high-res 8x MSAA render target, and I have a lower-res 4x MSAA render target. The 8x render target is a 1.4 scalar, so it's 2116 by 2352. It's 342 megs of GPU memory for the MSAA color buffer, MSAA depth buffer, and the resolve color buffer. And at the same time, I also have a 4x MSAA render target and its color buffer and its resolve buffer at 117 megs. So I have a total of 459 megs per eye of just render targets. So this is why Source 2 is still using sequential rendering, because I want to render the left eye, submit it to the VR system, and then clear those render targets and reuse them. Otherwise, I have to allocate 918 megs of just render targets. On the GPU. And even if you have 4 gigs of RAM on your GPU, using almost a gig of that for your render target seems a bit extreme, in my opinion. And what we really want to do is go to a 2x scalar. And if we go up to 2.0, this is really my target, this is what I want to do. If you use sequential rendering, you can get away with only using 815 megs of GPU memory.